Okay guys, so we're going to look at another example here. I'm going to give you f of x, and it's going to be equal to x squared if x is going to be less than or equal to 1, and it's going to be equal to 1 minus x if x is greater than 1. Yeah, so why don't we determine what is going on there's only one place I'm really interested in, right? That's pretty small. People at home can't see that. There's only one really place I'm really interested, right? This is a quadratic. This is x squared. So it's pretty much, you remember from grade 10, please, that it's pretty continuous. You didn't jump at gaps or anything. And you know that this is a line, right? You know that, so that's y equals negative x plus 1. So that is this guy. There was no any gaps or jumps or anything with him, right? So you really know that if we're talking about continuity here, there's only one place that anything could be interesting, and that's at where they match up. Does that make sense? This guy's continuous everywhere. This guy's continuous everywhere. And we're going to talk more about that in our next couple of examples, but the only place that anything interesting can be happening here is where they match up. So let's take a look at this. What are the conditions for continuity? Well, it's the limit as x approaches a of f of x has to equal f of a. If you're thinking about getting a new tattoo, that's a good one. That would be great to see on someone's forearm or something. Yeah. Notice that this has three conditions. First of all, the first condition is, does the limit of f of x actually exist? That is the question. So to exist, I need a left-hand limit and a right-hand limit. So if I'm approaching 1 from the left, I'm going to be following this rule. And so using mega property with that rule, I'm going to get 1. And the limit, as I approach it from the right, using mega property, is going to be 0. Is that right? Yeah. So what does that mean? And you're done. Therefore, f of x is discontinuous at x equals 1, since the limit as x approaches 1 of f of x does not exist. And if you wanted to explain that even better, you could say the limit as x approaches 1 from the left of x squared is not equaling the limit as x approaches, well, you don't even have to have the x squared, you could just call it f of x, is not equaling the limit as x approaches 1 from the right of f of x. Period. End of conversation. Okay? And you're done. You don't have to go any farther. That's absolutely correct. Now, someone asked me a question just when the video was off, and that was, does that mean that if condition 1 is true, and if condition 2 is true, that condition 3 must be true? And let's just think about that for a minute. So let's have a function where condition 1 is true. So in other words, the limit as x approaches a of f of x exists. Okay? And let's think of a function where f of x is defined at x equals a. Does that mean that the third condition must be true? And the answer is going to be no. And I can show you a visual example. So here's one where the limit exists. I got no problems. Limit exists, right? We're good with that. Yay, nice limit. And I'm going to have it defined. Oh, look at that. Isn't that great? That's defined. But condition 3 is not met. They don't equal each other. So just because this exists and just because this is defined doesn't mean that we have a continuous function. Condition 3 is a separate condition all on its own. The only time condition 3 works is if where it's defined equals the limit value. Okay, we're going to take a break there for a little bit, and then we'll come back.